Hello, welcome back to another episode of pollys Introduction to Computer Networks. All right, so we have a super nice weather since last year. Today, great. Oh, hey, I think Jia Yi is Charlie. Wang Yi is Elaine. Nice. Gladdy. And Pei Yun should be Peter. Hey guys, I tried to memorize you guys' English names so that I had less trouble with pronouncing the name correctly. Smart, isn't it? Hi, Chloe, Yuzhen, and Jin Yang. I think, sorry, I probably didn't get the intonation right. I think the hardest part of pronouncing Chinese is the intonation. Yeah, 1、2、3、4声. Oh, that is hard. Okay, that is hard. But you know what? What is easy is computer network, and it is also fun, right? Before we start, let's go over what are doing this week. So we do have 3 quizzes doing, 5, 6, 7, and we'll work on quiz 5 today. And there's also a PA doing end of this week. That is PA number 2. Okay, so this one is obviously harder than PA 1, all right? So allocate more time into it. Okay. Something that's a little bit special in the announcement is this. This is the 3rd week of the semester, so the student list is finally settled, right? So Polly has generated this Google spreadsheet. Okay, so if you click into this link here, you'll find inside the spreadsheet there are actually 4 worksheets. Quiz records your progress of completing the quizzes. So this Q3 here, you see many of you receiving like 1 with the yellow highlight. The boxes with yellow highlight means that you receive extra credit. Okay, special recognition for the answer to that quiz. So those are usually for the answers that are thoughtful, unique, or in some quizzes fast. Okay, so in the repeating quizzes, quizzes that are repeating over the years, okay, those then I don't count whether you're fast or not. All right. And then there's a sheet recording the participation, and you will also see that every week Polly will record the participation in 4 categories. One is your participation on the YouTube chat. Okay, so you see Ting Jun, Qing Yang, Yu Zhen, you guys all earned 1 point, okay, by saying hello. And so there's a column recording your participation on Discord that including asking questions or sometimes answering questions for Polly on Discord. Or if you just simply post the solution on behalf of your team for some of the quizzes, you receive also a point for Discord participation. And then some of you might call in through Google Meet to the office hour. I also record that. And I know that some of you might prefer sending me emails because that is a little bit more private. Okay. And sometimes email is the best way to find Polly. Okay. And so you see that the participation, it can come in many forms, many ways. Okay. So that's participation. And the PAs. If you look at the PA number 1 column, you guys all pass a PA 1. Good. And last sheet is the semester grade. Hey, this is going to be empty throughout the semester until 2 weeks after the final exams, where we have everything computed. Okay, and this is the place you look up for your semester grade. Okay, all right. So there's one thing I like to ask you a favor. Okay, please check the team number and the student ID. Okay, and let me know that whether your ID appear in your team. Okay, and so you see that I also remove some of your teammates because they do not appear to be registered officially for the course. So I check the university record. If I accidentally remove some of the students, guys, let me know, because I think the university system is a little bit shaky. The update can be slow. Okay, so in that case, those students who are adding later on last week, I might not see your name appearing in the list I downloaded yesterday. So I might have accidentally deleted you. And so the view I see seem to be different from what you guys see. So check the list for sure. And let me know if the team number or the student ID, there's anything being mistaken. All right, and that takes us to the first set of videos today. Okay, last week we started talking about the core of the network, core of the internet. It's actually a bunch of routers interconnected. Okay, but you see, to pass data along such a very densely connected core network, there are two design philosophies. Last week we talked quite a bit about the first philosophy, circuit switching. Today we'll talk about the second one, packet switching. And the two of them actually contrast each other. If you recall, in circuit switching, the key word is what? Reservation, isn't it? We reserve a circuit so that we could pass data smoothly. And because of doing that, we will need a little bit of time at the startup to set up a call, to set up a circuit. Okay, packet switching here is the opposite, and it promotes sharing. Okay, so here are the details of packet switching, the idea, what's nice about it and what's not so nice about it. Now let's discuss more about packet switching. The mechanism is very simple, right? We simply cut the data into small packets, and as the link is available, pass it out. So each of these small packets will go on the link in full bandwidth. So if you consider L being the size of the packet length, and R being the link bandwidth or the link rate, the delay, this being small, this being large, to send a packet very small. This is one advantage. And then think about this: if you get two users, A and B, both are generating data and both are sending these packets out. If A is idle, not sending, and B comes up with data, B can send out, no problem, and in full link bandwidth. Similarly, if B is idle and A has data, no problem sending out. So there's no such a situation in circuit switching when B allocates all the resource, gets all the resource, and A having data to send, but A didn't get any resource. As a result, B sitting idle, occupying all the resource, and yet A having lots of data wanting to send, not getting anything. Okay, so there's no idle waste there. Last is maybe a little bit less obvious. You see, bandwidth is used as full, so there's no need of dividing the link bandwidth into pieces. So the mechanism is also simple. Okay, being simple, there's no idle waste, and there's no call setup, resource reservation process required. Okay, packet switching can potentially be very efficient, especially for short data streams. Think about the resource reservation delay, the call setup time. It can be pretty long, and if you have very short data stream, then hey, the overhead relative to the entire need of sending data is high. So you can probably imagine now, data network, internet. At the beginning, we were just sending really short emails. It doesn't make a whole lot of sense just to send an email and you go all the way to set up a circuit. So another advantage of using packet switching is also because of the user demand. Now let's look at what's wrong with packet switching. First of all, we will have resource contention because there's no reservation mechanism. What if A and B, they all have a lot of data to send. So the resource demand is beyond the available resource. So we call that situation network congestion. In that particular situation, packets will have to queue up at these routers and wait for link queues. So you see here, wait, the keyword. Delay here to transmit a packet is short, but there could potentially be way that is a little bit uncertainly long. Okay. And hey, packets will get queued. What if there's not enough space in the queue? Packets also get dropped. So in packet switch network, we do have substantial delay. We could have substantial packet losses. One big disadvantage. Another disadvantage is here. One is a little bit subtle. In packet switching network, there's no circuit being established. The way we send packet is that you forward it out on the link. The next router will need to pick up everything. So you need to wait until the entire packet is received. The next router will need to receive the complete packet before the router can further forward the packet. So this is called store and forward. So the router action there passing packets is store the packet first and then forward the packet next. So this mechanism here is determining how packets are moved, okay, one hop at a time. Meaning you have one of these L divided by R every hop, every router. All right, so store and forward. Okay, so it's a new term. In the next video, let me use an example, okay, to illustrate so that you know a little bit better what I meant by store and forward and hop until the destination. So here let me illustrate the store and forward effect to the end-to-end delay. So consider this scenario. The source is over here. Okay, user typing up things and generating these small packets, 1, 2, 3. One router here in the middle and receiver on the other side. And each packet here the user is generating is L bits long and the link bandwidth is RBPS. So you see, to send this big packet over the link at this speed, this is the amount of time that's required. And a packet switch network, we need to store the packet entirely before forwarding. So entire packet needs to arrive at the router before it can be transmitted further. The end-to-end delay will be what? 1L divided by R for this hopping. Because this guy, to send it out, it requires L divided by R. This router here receiving it waits until all is received, and then what? Send it out again. That's another L divided by R. So if L is 7.5 megabits per second, R is 1.5. You see, each hop, 5 seconds. 2 hops, in this case, how long? 10 seconds. 3 hops, the longer, the more hops you have, the delay of sending the packets longer. This is different from circuit switch network. Bits can be streamlined. Okay, there's no need to store a bunch of bits first before forwarding it. Okay, that is saying that each bit arriving here gets out quickly, so there's no hopping. It's just the propagation delay and the transmission delay, L divided by R, from the first hop. This slide is to illustrate congestion. The scenario is A and B, 2 users generating packets. A generating green packets and B here generating blue packets. And you see these packets are generated as user A and user B are typing things up spontaneously. So green and blue, they will kind of bunch up or multiplex in a random order. Okay. Unlike in TDM, time division multiplexing, Everything goes rotating, rhythmic. And this, okay, having some sort of spontaneous behavior in it is statistical multiplexing. Okay, so on packet switch network or on the data network internet, yeah, packet kind of, multiplex to each other randomly, spontaneously, depending on how they are generated. Now let me draw your attention here. The router. You see packets in case the outgoing link bandwidth small. And incoming link here, this is 100 megabits per second Ethernet. This is only 1.5 going out. Chances very high, A and B, if both of them actively generating lots of packets, yeah, the packets will have to wait here in the queue before they get the link queues. And if there's not enough space here for the queue, the next one, the green one coming here, will need to be dropped. But there's no memory space to hold. And those packets waiting in the queue, yeah, it depends on how long the queue is as they comes in to the router. The queuing delay can vary. It can be a little uncertain. But transmission delay, the time it takes to go on this link is always the packet size divided by what? 1.5 megabits per second. And we use the full link bandwidth. So transmission delay here is very easy to get. All right, so packet switching is essentially here two keywords. Packets get mixed, right? And as they arrive at the router, they store and forward. So mixing packets for packets, mixing packets for packets. Okay, that's packet switching. Next, let's try to compare circuit switching and packet switching first, quantitatively, through an example. Here, let me use an example to illustrate. Packet switching actually outperforms circuit switching when there are more users and each of these users are not exactly very active, sending short messages only each time. All right, so scenario is very simple. Okay, we do have a network of end users and they're behind this router. Going out of the router is a very low bandwidth link, 1 megabits per second. And each of the users is behaving this way. When they're active, they do need a lot of bandwidth, 100 kilobits per second. But they're only 10% of time active. In a circuit switch network, in order to satisfy these 10 users, and each at maximum requires 100 kilobits per second, so we reserve 100 kilobits per second to each of the users. And how many users we are allowed to reserve bandwidth? This is 1,000 kilobits, so we can only allow 10 users, okay, 10 circuits. But in packet switching, you see, the users are only active at 10% of time. Consider this scenario. If we have 35 users, right, the only situation that these 35 users will have trouble sending data out is when there's at least 10 users being active at the same time. So what is the probability of these 35 users and more than 10 of them being active at the same time? If you do the calculation, you'll see that it's very low. So 99.9996% of the time, in packet switch network, 35 users will do well. No trouble. So if you do have a lot more users and each of the user needs just a small portion of time to send data, which one would you pick? Circuit switching or packet switching? It's quite obvious, isn't it? And oh, by the way, anyone here knows how to derive this value? The probability of 10 of the users being active at the same time, given the active rate is 10%. All right, those who know how to calculate that 0.004, do post. How about ask us anything underscored? You earn extra credits for them. Okay, good. So from that example, you see also a little bit that packet switching is kind of a gambling. There's a risk that when you need to send data and there's not enough capacity sending data. But circuit switching is to, hey, ensure everything is going to go well if you are allowed to get in. Okay. Oh, okay, we have questions popping up. So Li Chang, Johnny is wondering how the size of the queue are for general implementations. Hey, Johnny, you're asking a question Polly will talk about in chapter 4, in fact. Yeah, I think that's chapter 4. Yeah, when we are talking about the router, what's inside the router, there's a component called buffering. Okay, so in that component, we will talk about how do you determine, right, how big the buffer is. By the way, buffer is a way of calling the size of the queue. Okay, buffer size, queue size. Okay, buffer is essentially a queue. It's a major question. There is a simple way of calculating it, and then there's an extended way of calculating it, and then there's a way of trying to reducing the amount of buffer you need to allocate if you are sure that the traffic going through this router are mostly TCP traffic. Okay, so TCP is another notion that Polly will talk about in chapter 3. Okay, so Johnny, you have to be a little bit patient. But usually it has something to do with the speed of the link that's going out of that queue, and how long it takes to for a packet to finish traveling that link. Okay, so you kind of try to keep enough space to handle a single pass of packets might stuck on the link. Okay, Sean, very good. And Dole, let me see. Exactly. Okay, great. So Sean, yeah, that is the trick. Yeah, binomial distribution, definitely. But Dole has the perfect solution, entire exact solution. Oh, okay, same as Yuzhen. Okay, great. All right, so next, hey, we just compare the two philosophies quantitatively. Okay, so you see that PS taking some risk, but CS, no. I want to make sure that everything is safe as long as I'm promised, okay, to go on. Now, let's compare them qualitatively, okay, and through a quiz, okay, quiz 5. All right. So let me go to the whiteboard more. Sorry. Now you see. Okay, you see the YouTube back end there. Okay. Now, good. So this is quiz 5. Okay, it's a little bit interactive in whiteboard mode so that you can probably follow my description of the quiz a little bit easier. Okay, circuit switching. You see keyword again, reserve. So we reserve a circuit network resource for data. Okay, let's try to analyze, okay, packet switching, circuit switching by relating a data network to other kinds of network. For example, yeah, the water network. Instead of transferring data, let's transfer water. Okay, so circuit switching will be a little bit more like building pipelines so that we could send a stream of water smoothly without overfills. Now, packet switching, keyword is what? Hey, mixed and pass. Mix and pass. Now, to transfer water, okay, a similar way to packet switching to transfer water will be more like this, right? We put the water in buckets and have people lining up, and so people will be taking buckets of water from someone and pass it to someone else. All right? Yeah, so you see in water network, hey, there are two ways of implementing transferring water. Now, Q5 is asking you to try to exercise your association. Consider other analogies we see every day that you guys are familiar. Car network. Okay, so we see cars traveling on the streets. Okay, Do you think the car network, okay, this network of transporting cars, is more circuit switching or packet switching? What about a train network? Okay, for either one of these, whichever answer you would like to take, which side you want to take, tell us why. All right. And Q3. Now, this is, simply answer based on what you feel. Between circuit switching, packet switching, one is reservation based, the other is to promote sharing. Which one you like better? Okay, and why? All right, so this is one of these open-ended quizzes. So you'll be allowed more time. So you guys have 10 minutes. Okay. See if you can find your teammates. If they are not easily reachable, think within yourself. Do you think the car network is more circuit switched or packet switched? What about train network? Okay. When you have an idea, go to the Discord. Week 3 quiz 5 board. Oops, sorry. Wrong key. And stop typing up your answer there. All right. Okay, so let me start counting the time. 10 minutes. Go on. Right. So, hey, some of you might still be typing things up, but I mean, let's check out some of the answers from teams that come up with something faster. So, Peter, representing Team 11, was saying, yeah, the car network is a little bit more like packet switched, and the train circuit switched. All right. And I think Yi Seng is trying to respond by saying that the car network allows every car to pass one by one, so it's more like packet switch, so passing, right? A mix pass, a mix and pass, mix and pass. But the train, you kind of need to build all these railroad first before you send a train, okay, on the track. It's a little bit more like a circuit switch network, right? I think that makes sense. And I think Team 11 and Team 6 here both like packet switching better because it will be more convenient, right? In the off-peak time, okay, you get to use the entire resource. Okay. In the rush hour, maybe use circuit switching. So maybe one can implement the network with both options. When it's light traffic, then run the packet switch mode. When it's congested, then run the circuit switching mode. This actually reminds me of a car network that is the highway car network. I think during the long weekends, holidays, right, the highway was always like, you know, a gigantic parking lot. So when the traffic volume is high, you see that these ramps getting on the freeway, there's a traffic light being implemented. Only when it's green, then you can go on. Otherwise, you cannot. Okay, so that is a way of simulating a circuit switching like circuit switching like behavior in a more or less packet switch network. Because when it's red, you're rejected at all to get on the network. But a reject call, a rejected use of resources, very circuit switch network. All right, and let's see. Jin Yang representing Team 10 here says, packet switching for car because you drive on the road when the road is empty and you can also go fast, kind of. And CKT, since train's departure arrival is scheduled in order. Okay, circuit switch for the train network, I guess. And we like packet switching more because IPOAC is based on packets. Okay, so yeah, that is a joke that you need to. Oh, okay, that is a joke that you need to know IPOAC to appreciate. Okay, so if you're curious, look up Google IPOAC. Okay. Yeah, so I see Team 10 likes a very special network, and because it's a packet switching, therefore you like packet switching. All right. And Loretta here representing, okay, we're missing the team number, but okay, Team 2. Packet switching, circuit switching, and then you like packet switching more. Oh, wait. Oh, you like CS more, circuit switching more because, okay, a packet switch network, going on a packet switch network, everyone is taking a risk. Yeah. CS, it's reserved, right? So you feel safer. Okay. So in case you are doing a long distance travel and you are traveling to an important meeting that you cannot be late. I can totally relate. Okay. Team 8, Ziqin is saying packet switching because you can decide when you want to go. Okay. This is a advantage that in fact this is in fact an advantage of a packet switch network, right? You can go faster. You can also go slower. As long as there's some spare resource in the network, you can go anytime. Unlike in the train network, it's a dedicated time, and you are only allowed this time frame to travel. Okay, very interesting, very unique. Circuit because no matter if there are passengers, the train has to go at the time it's scheduled. And you guys like packet switching more because it's more flexible. It is more flexible. Okay. And Yujin Pro is saying packet switching because cars don't need trail. I see. Yeah, the infrastructure cost seems also lower, isn't it? Yeah. And I mean, maybe just a little bit of queuing time is fine. I think sometimes when the queuing time is fixed or predictable, then it might serve the purpose of many of the guys want to take a circuit switching service, isn't it? Trains has a fixed time schedule. Yeah, exactly. It's a little bit more rigid. Yeah, you guys like PS better? Since it's obviously not PlayStation, but packet switching, since it's more flexible and fit for more situations. Yeah. So it seems that PS is obviously a better choice, unless there is condition, isn't it? Okay. And it might be lower cost. It should be lower cost as well. Team 1, Steven is speaking for Team 1, car network, packet switching. Google Maps and routing to places around the city, we choose the most. Yeah, exactly, right? You can look for a route, and with that, you just go. Or you could have your phone running Google Map in the car, on the dashboard. Then you can be rerouted anytime. It's very easy. And so it's not a fixed path. Unlike circuit switch network, it's a fixed circuit. So that's how you think the car network is more packet switched. I see. Makes sense. Train network, circuit switching, it's always a fixed route, okay, for a particular train. Yes. Okay. Team 1 also prefer packet switching. Hey, okay, only one team preferring circuit switching now. Uh-oh. Yeah, it is a little bit more cost effective and efficient in most cases. You know what? If you think about air travel, it's actually a mixture of circuit switching and packet switching, isn't it? So for the guys in the first class or business class, right, they have like a dedicated channel when they're boarding. And those sitting in the economics, like you guys, students, well, you know what? Professors are generally poor, and we are regulated. Okay, when we're on business trips, we take the economy class. Okay, so hey, we packet switch. Okay, as we are boarding the planes. So indeed, we've seen systems that have a mix of packet switching and circuit switching implemented and working seamlessly together. Team 7, Oscar, car network. Each car shares the same road. Need to wait beside the road. Okay, so you can wait longer if you want. Yeah. So it's not like fixed and at a fixed time. Definitely. Train network, more circuit switch because it's the same route, I guess. And if there are no trains on the track, it is resource idling and wasted to some degree. I guess when you are arranging trains on the tracks, sometimes you give a longer amount of time between the trains for safety reasons as well. But during the night when there's low traffic, you schedule less trains on the tracks. It is, you can consider it as a waste of resource. So that track is used not entirely, not fully occupied in the light traffic periods. That is the exact point of when we say there's idle waste, okay, when we talk about the characteristic of circuit switching. And Oscar favor PS because it seems to work for most of the cases. Ming Luan, car network. Yeah, so you can think of the roads like the network links, right? Yeah, and you can connect to other, you can travel other links and still come to the same destination, okay? And I think there's a team previously pointing this out as well. Train network, more circuit switching. Yeah, because of the track, isn't it? And it's fixed. And the train, when it's traveling, there'll be no other cars there. A train will be mixing with, definitely. All right. Okay, good. I see Charlie is trying to address a question I asked earlier. Team 5, very similar. So I think we are converging, right? Car network, we think more packet switching. Train network, more circuit switching. And you see the design of the use of these two philosophies in networks that we already know, we are familiar with. So guys, the point of this quiz is so that you try to exercise your association. Many of the things, many of the components we see in a computer network, you probably find an analogy somewhere in daily lives. You can borrow solutions you know already, okay, from daily life to a data network or to a network you are designing, okay, for the future, or for some very special content that you want to transmit, okay. Great. Okay, guys, we don't have all the time to go through all the teams. So later on this semester, you might see also that probably need to cut the walkthrough of the quiz solutions short so that we leave some time for Q&As and for the videos. Okay, so let me come back to the chat because I think Mark is asking something. Would this example also be considered CS? We reserve track for train only from point A1 to A2, and for certain time slot where train is going from point A to point B. Hey, Mark, I think that is very circuit switch because you are reserving, but the reservation you are making is two-dimensional, isn't it? Physical track and the time. This is a more advanced way of making reservations. So you can think of a circuit switch network, okay, such as a telephone network. You can make reservation and create a circuit this way, as you have seen in a train network. Exactly. In fact, there's one particular way of sending data onto wireless network called CDMA. Okay, it's called the code division multiplexing. Hey, earlier, right, when we were talking about circuit switch network, or when we were talking about cable network, right, we divide the frequency band into smaller subbands, and we do frequency division multiplexing. So we could send data in parallel across these subbands, okay? And TDMA, okay, time division multiplexing, is to do it at the time dimension. Mark, you can do a mix of the two dimensions. And that is exactly what CDMA is doing. CDMA, I think it was used in G3. G3. I think most of you guys are probably still using, 3G wireless network. Most of you guys are probably using 4G and some of you using 5G. Yeah, that wireless protocol for wide area internet access used to be just 3G, and 3G is using a CDMA. It's a code division multiplexing that's actually taking a combination of time and frequency. And that train network is quite advanced if you think about it that way. It's a spatial temporal, okay, mixed multiplexing. All right, so I hope that I demonstrate that computer network is easy in a way that it's just like any communication network. Okay, it can be human communication, it could be car communication, it could be air communication, it could be water communication. Okay, those networks, you've seen how people solve all sorts of problems. Any of those solutions there, you can borrow and solve the problems we will see in data network. And some of the mechanisms we will be talking about starting from chapter 2 and on. You might see them being familiar and find analogies in real life. Okay, and you'll see it's not hard at all. All right, you know what? That is all the time we have. All right, so hey, Loretta, Wang Wei, I think, Chloe, right? Chloe, team 4, Dorley, team 9, and Gladys wants to add something to what team 2 has already wrote. Yeah, I'll definitely go over the rest of you guys' solution. All right, good. With that said, let's call it the end for this lecture. And guys, come 10:20 tomorrow morning, we'll continue to talk about packet switching. Okay, so far we've learned about circuit switching and packet switching. I'm pretty sure that with quiz 5, the two notions are very clear. Okay, and we will not be talking more about circuit switching, as in fact the internet is designed based on packet switching. Okay, so the next set of videos coming up is to tell you more about packet switching. Okay, why don't we just send a big message at once? Why do we cut it into packets? Why? And hey, why don't we just stream the data bit by bit like circuit switching? Why do we store and forward? Why? So come tomorrow morning, then you won't miss the answers to these two whys. Okay? All right, so with that said, I say goodbye. See you tomorrow. Okay, bye. See ya. Okay, bye. Very good. Connection is always established. Yeah. So you always ensure that there will be no other trains on the track. Prefer circuit switching. Totally understand, Florida. Okay. Feel free to take your stand. Yeah. If you like CS, yeah, argue for it. If you like PS, argue for it. It's okay to be a minority. Very concise answer. Like it? You don't reserve a road, okay? Well, hey, maybe for visitors, important visitors from foreign countries, and yeah, they need to travel really fast from the airport to the presidential hall, maybe. Yeah, I think it's thinking about resource. Very good. You guys are great. Very thoughtful. Keep this going. I guess, yeah, buses in some countries are circuit switching. But in Taipei, not exactly circuit switching. Alright. Okay, bye. Ending the stream now.